Hello. In this lesson, we'd like to talk about the area between curves, especially between two curves in particular. So first of all, we're going to review what is area under the curve. And we talk about a Riemann sum, okay? So in order to find the area between the curve and x-axis, what we did three steps: partition, forming Riemann sum, and then taking limit. And we know that most of the functions we're dealing with, they all have area under the curve. In other words, they are integrable. Say, when we look at this situation, okay, we like to see how a typical slice area is constructed. So in this case, you can see the typical slice area is this piece. This is the typical slice. This is the typical slice. Okay. Let me change the color. Let me change the color so you can see better. Or make it thicker. I'm gonna make it thicker. Okay. So the typical slice here is this piece. Once we identify the typical slice, okay, the typical slice, and then we are going to mark it. Okay, the typical slice is this piece. Okay, and the height, okay, the height is f of xi star, which is right here, f of xi star. That's the height of the rectangle, and the width of the rectangle is delta x. Delta x. Delta x is how wide the subinterval is. Once we are able to form the typical slice, and we're just one step away to get to the definite integral. So this is the definite integral here. So you can see the interval in consideration, right? We have many slices, and all of these slices is, part of the Riemann sum, and we add them all up, and the Riemann sum runs from A to B, and the integration goes from A to B, and f of x, which is directly transformed to f of x here, and delta x turn into dx. And that's kind of, waving hands just to, after taking limit. Okay? Here we should insert a limit notation. Limit as n approaches infinity, or delta x approaches 0, right? So either way, so we get this integration, okay? So it's very important to identify the typical slice area. When we try to identify the typical slice area, first thing first, okay, it's a function. What does it mean it's a function? A function, okay, so that's a review. What's the definition of function? A function is a rule that from each input, assign each input exactly one output. Exactly one output. So the function is a rule. It assigns each input exactly one output. And that is the vertical line test. If you draw a vertical line, you're going to get, exactly one output. So that's the function. That's the blue curve right here. So to apply this technique, you need to observe that this area is bounded by this vertical line, okay, which is x equals to a, Okay, so this vertical line, which is x equals to a, and the other vertical line, which is x equals to b, which is the vertical line right here, right? This vertical line. So the area we're looking for is really this piece. Okay, let me change it to red. Okay, it's right here. So this piece, there's one straight line, two straight lines, and three straight lines. Only one side is curly. Only one side is curly. When we apply this technique, we are, construct the typical slice area, and then we take limit. We got the Riemann sum, we take limit of the Riemann sum, and we get the definite integral. Okay, and this kind of method works for a three-sided straight line and one curve, and that curve is a function which passes the vertical line test. So now let's look at an example that we did before. Okay, this is example, I call it example number 1. Okay, we are to find the area between the curve. So find the area under the curve on the interval between 0 to 8. Between 0 to 8. So we have this curve, and what's the area between the curve and x-axis? The area underneath the curve, meaning the curve between the curve and x-axis. That's what we need. So in the process of constructing Riemann sum, okay, we're going to have typical, so we're gonna, first identify there's three-sided straight line, okay? So this side, that side, and the third side. Three-sided straight, and the rest is a curve. And then we look at the typical slice, right? A typical slice could be like this, right? It could be like this, but how do we construct this typical slice? How do we find so this is the one function, right? It passes a vertical line test, obviously. So for any one of these typical slides, you imagine their partition, right? So the height. So let's mark the height. We get some height. Okay, so this is one height, right? This height is f of x, okay? And there's another height is also f of x because we're using the same function, f of x. So when we look at that typical slice, okay, typical slice. And that typical slice, the height is f of x. Sometimes it's negative, sometimes it's positive, that's okay. And the width is delta x. Delta x, after taking limit, that's dx. And then we're going to integrate between 0 and 8. So that's how we construct that integration. Then you say, well, that's pretty straightforward, right? But we're going to remember this technique. Remember, this is how we do it, because we're going to get to see how we find area between two curves, right? So the question is going to get a little bit more complicated. So let's finish this example. In this example, of course, the function is x squared minus 8x plus 7. We apply fundamental theorem of calculus, and we evaluate between 0 to 8, right? And you can pause and take your time to finish the question so that this question is done. So we get the final answer. The final answer actually is a negative number. Well, if you look at the curve and this area underneath the curve between the curve and x-axis, it's no surprise because it looks like the negative area is way larger than the sum of the positive area. Okay, so now let's move forward. How about finding the area between two curves? How do we find area between two curves? Okay, so I'm going to move this title under. How do we find area between two curves? So now suppose we have two curves. Two curves, they're both functions, right? First thing first, they're both functions. Functions means they pass the vertical line test. They pass the vertical line test. Now, between A and B, we have two straight sides, right? You can see the straight sides A, x equals to A. So I'm going to mark it. Hold on. There we go. Okay. So this side is A, this side is B. What's different from before is that we have three-sided straight lines. So this time we just have two-sided, which is A, x equals to A, x equals to A, and x equals to B, only two straight sides. And the other side is curvy. So we're going to construct Riemann sum. We're going to construct Riemann sum and these typical slice. What is the height of this typical slice? The height of this typical slice is f of xi star subtracting g of xi star. So we imagine, after partition, we have all these slices from A to B, and that's the typical slice. Once we get the typical slice, and we just take limit, okay? We're going to just take limit right here. Hold on. We just take limit as n approaches infinity. And we got our definite integral. Okay. So each time we are constructing we're constructing this, we need to be aware that this typical slice is under one curve consistently and under the other curve under consistently. So this piece, right? So we have all these slices, but all these slices under the curve purple, and it's also above the curve blue. And these two functions, these are functions consistently. Okay, so we're gonna remember this, and we're gonna apply this to some examples. So now, how do we find area between the curves? And so here's the formula. If it is under two functions, all right? So now, let's look at the first example. The first example we have here is that the red is e to the power x. And the blue is y equals to x. And the area we're interested in is between these two curves. Okay, it's between the two curves. One is curly and the other one is a straight line, but it's not horizontal nor vertical. So it's just, it's a normal line. So we have two straight sides So now we have a function above and we have one function below for the interval from 0 to 2. So if we are to construct a typical slice, so that's a typical slice, okay? The height of this typical slice obviously is a function from above subtracting the function from above, which is the red function, subtracting the blue function, the blue, okay? And this height is the same for from 0 to 2. So it's consistent, So the red function obviously, so our typical slice, okay? Our typical slice is e to the power x subtracting x. So that's a typical slice. And the parentheses multiply delta x, right? And so if we convert it directly to integration, we convert it directly to integration and integrating from 0 to 2. Okay, so that would be the area. Okay, that would be the area between these two curves. So I'm going to mark it. So that's the area between the two curves. So this is the piece between two curves, right? You can see the rectangle slice can go up and down this entire between the two straight line, this piece and the other piece. Okay, let me mark it here on this side. Okay, this side, the boundary is x equals 0, which is y-axis, and the other side, the boundary is x equals to 2. We have two straight sides and two curly sides, So this is a simple example to demonstrate how to find area between two curves. And let's finish the question. Okay. Typical slice, actually, I should put it here. Okay, the typical slice, I will write the typical slice this way. Okay, or you can use delta x. Okay, so area between curves. Area between curves. So this is how to set up the area between the curves, and then you verify whether you got it right. Okay, so let's continue to finish the question, and we're going to apply fundamental theorem of calculus part 2. And the antiderivative e to the power x, of course, is e to the power x. And the antiderivative of x is x squared over 2. And all of these okay, and evaluate at 0 and 2. Okay, continue. We substitute. Okay, we got capital, subtracting. One is x equals to 2. And the other one is 0. Okay. And we're almost done. E squared minus e squared minus 2, subtracting, this part is 0, so subtracting another 1. In the end, we got e squared minus 3. Finished. Okay? So find the area between the two curves. We want to make sure that we use we have the same curve consistently above and below, right? And there's a true straight size, vertical straight size. Could it be horizontal straight size? Yes, it's possible. So that'll be another case. So this example is, in this case, we're integrating with respect to x. We make that distinction now because in other lessons we're going to talk about how do we integrate with respect to y, right? This example is integrating with respect to x, and in our earlier example, that is also integrating with respect to x. Obviously, it's dx. Okay. All right, let me tidy up this a little bit. So let's look at another example between two curves. Example number 3. Okay, so this piece obviously is absolutely between two curves, and these two curves are given, and the green one is x squared, the red one is 2x minus x squared. By this time, you have the picture. It's pretty obvious the area bounded is really the area between the two curves, which is this piece. You don't even need to draw the slice because you have one curve above and the other curve is below, right? So we can just set up the integration to find the area underneath between the two curves from 0 to something else. So we know what's under and what's above, right? It looks like it's 1, but are we sure? Okay, the curve above is 2x squared minus 2x minus x squared, and the curve below is x squared. So we can certainly set up like this, but can we be certain the intersection? Because it looks like we need to find the point of intersection. So before we can go ahead with the integration, right? We have to find the point of intersection between the two curves. Between these two curves. And how do we find that? Of course, we're going to solve system of linear equations, right? So we basically solve system of linear equations. Okay, we do need to know how to do this because sometimes the intersection is not so clear. Okay, so we're going to use this opportunity. So we're going to set up this. One is y equals x squared, right? I'm going to put it as the system of linear equation, just like this. Okay, the second one, like that, right? We don't need this. We don't need that. So we assume, because at the point of intersection, x equals to y, right? So we set y equals to y. If y equals to y, x squared will equals to 2x minus x squared. Okay, so let me write down the arguments. Okay, at the point of intersection, okay, the coordinates are the same. Are the same, x equals to x, y equals to y. Because we are looking for the point or sometimes points of intersections. Okay, so we assume x equals to x, y equals to y on both curves. All right, so let me get rid of those stars. Let's first find the point of intersection. So once we get this, we can solve for x. We can solve for x. We're adding x squared on both sides, so we have 2x squared. Okay. Then we can reduce the 2, right? We can reduce the 2, dividing both sides by 2. And then what do we do? What can we cancel the x on both sides? The answer is no. Okay. Don't cancel x on both sides because we don't know if x can be 0. All right, so what should we do? We should move them to both sides. We can make 0 on one side. We get x squared minus x equals to 0. And this looks like it's a pretty simple situation of, algebra questions, right? So x times x minus 1 equals 0. So either x equals 0 or x minus 1 equals 0. Right? So we get x equals 0 or x equals to 1. So we have 2 points of intersection. We have 2 points of intersection. And what are they? Well, one is 0, comma, well, you can plug in x equals 0 in either one, you get 0, 0. And the other one is 1, comma, plugging 1 into one of these, you're going to get 1, 1. So these 2 vertical lines, 2 straight sides, right? So this is straight sides on this piece, so of course there's 1 dot. So the integration is going to be from 0 to 1. Okay, so let me mark this point. Okay, there's a point right here. It's 1, 1. It's a dot. And there's another point, which is 0, 0. And these 2 are the point of intersection. Okay, so let me just mark it for you real quick. Okay, so this one is 0, 0. And the other point is 1, 1. Okay. Here we go. So we have 2 points intersection and we're integrating with respect to x. So this is dx. And then we're going to finish the integration. Okay. To finish the integration, we're going to combine the like terms, right? So this minus x squared twice. So we have a 2. And we can, and then the antiderivative for 2x is going to be x squared, right? And the antiderivative of 2x squared is 2/3 x raised to the power 3. And evaluate it from 0 to 1. Right? So plugging 0, we get 0. So we just have to plug in 1. Right? Plugging 1. So this is 1. And that's multiplied by 1 to the power 3. So in the end is 1 minus 2/3 and that's going to be 1/3. 1/3. Okay, so that's the whole of the question. But look at the second example, the third example we have here. Obviously, we have an additional step. So besides identify the situation as the area between two curves, you also recognize that we need to find the points of intersection, because the point of intersection was not obviously given. So in some cases, we have to find the point of intersection. The point of intersection was not obviously given. Okay, so we use some algebraic technique to find the point of intersection. Okay, so let's look at the next one. Actually, it should be called example number 4. Okay. Example number 4. 3 changed to 4. Okay, we want to find the area between the sine curve, which is the blue, and the cosine curve, which is the red, between 0 and pi over 2. Between 0 and pi over 2. So we have two curves here, and the area of our interest will be between the two curves here, right? Between red and blue on this piece and on the other piece. You can see the area between the curve. On the one, we want to find the total area, which is, above by one function and the other one by the other function. And we can also see that on this piece, the red is above. On the other piece, the blue is above. And if we test drive our, typical slice, right? So obviously the height is different. The height is different. On the typical height on the one side, okay, that's going to be on this piece, the height is red minus blue. Okay, the red minus blue, that's the cosine x minus sine x. On the other piece, the blue is above. So it's sine x minus cosine x. Okay, let me change it to the proper mode. So sine x minus cosine x. And also, we don't know what this point is, where the curve intersects. So we need to find the point of intersection. Between these two functions, between sine x and the cosine x. And of course, we know sine x and cosine x, they can intersect at many points, right? But we are only really just interested in on this particular interval. That interval is 0 to pi over 2, because that's the part we're interested in. So we just need to find point of intersection on this interval. So how do we do that? Well, at the point of intersection, sine equals to cosine, right? So so that's why we said it's sine x equals to cosine x. Okay, and you probably have guessed it. When does sine x equals to cosine x between 0 to pi over 2? Well, that's when x equals to pi over 4. You can use unit circle, or you can also use some other algebraic techniques. Okay, so here I'm not going to spend too much time on the technique of solving trig equations. Okay, So we use our common sense and, basic understanding of function. So we find the point of intersection. So that point of intersection, okay, when x equals to pi over 4 and sine pi over 4, so the y equals to, so sine pi over 4 equals to cosine pi over 4, and that equals to root 2 over 2. So when we're going to mark that point, okay, we mark that point, so pi over 4, and then it's root 2 over 2. Root 2 over 2. So it's a red dot. It's right there. That's the point of intersection. So this rule, cosine x minus sine x, is for the area to the left. And this other piece is to the area to the right. And what is the interval? The interval, okay, the interval will be, let me make it thicker. The interval will be from, one is from 0 to pi over 2, and the other piece will be from pi over 2 to pi over 4 to pi over 2. So right here in the middle is pi over 4. So that point, okay, so that point is pi over 4. Okay, so to find the area to the left piece, we're going to set up the following way. We're going to set up right there, okay, from 0 to pi over 4. Okay, and the function will be cosine x minus sine x. And with respect to x, dx, right? Because the width is dx, delta x here. On the other piece would be the area, right? It's still integration with respect to x, but this time is pi over 4 to pi over 2. Okay, so this other interval. On this interval is the function sine x minus cosine x dx. So that will be the total area between these two curves. And so the total area, we're going to have to add them up. We're going to have to add them up. And we're going to finish the rest. Okay, so let's see. We have everything on the screen. I'm going to write vertically, because if I move up and down, we're going to get a messy situation. And then we're going to work on the antiderivative. The antiderivative cosine x is sine x. Subtracting the antiderivative of sine x is negative cosine x. So it's going to be plus cosine x. Okay, so for the first piece, okay, evaluating from 0 to pi over 4. Okay, so I'm just copy this little thing and move it here. Plus, okay, we're going to get another antiderivative, and we're going to evaluate it between pi over 4 to pi over 2, right? Pi over 2, so to remove that, replace that with a pi over 4 to pi over 2. The antiderivative of sine is negative cosine. The antiderivative of cosine is sine. Okay? And then you just plug in the numbers. Plug in the numbers. Okay, so I'm gonna put this on here. Okay, so we're going to evaluate this piece, sine this piece, applying fundamental theorem of calculus part 2. Okay, so we plug in pi over 4 for the x's and 0 over here, plus the other piece, right? On the other piece, if you like, you can take out the negative sign, actually. Or you can just keep it, okay? If you want to keep it just straightforward, just keep it. So, and this is going to be evaluated from pi over 4, right? So this is going to be, let me see if I can copy and paste and put it there. Right there, it works. Subtracting, and still keep that. And this piece, put it there. Okay, wait, no, sorry. I think I need to remove those because here is pi over 2. I removed it. There we go. Okay, so I want to keep the integrity of the whole thing. Pi over 2 will be substituted on this piece. And you guys probably can do it faster than I, because I have to, I'm just slower. Okay, so that's the major plugin. Okay, setting up and then finish the integration. Okay, so next we're going to finish this, but I have to clean this up. I have to clean this up. Let's see. Can I do it not without? Okay, let's try this. Okay, try to keep everything together. Okay. So sine pi over 4 plus cosine pi over 4, that's root 2 over 2 twice. Right? That's root 2 over 2 twice. Excuse me. Sine 0 is 0, cosine 0 is 1. So we have a minus 1. Okay. Let me move this over. Right, move this over. Right, so this is better. And so we finished this part. And the next part, right? So we got a negative pi over 2, sine pi over 2. I mean, negative cosine pi over 2. Cosine pi over 2 is 0. Sine pi over 2 is 1. So we got plus on the first bracket, right? It's minus 1. Subtracting the second bracket. Right, so from this bracket, it's minus 1. The second bracket is that we got a cosine pi over 4, that's root 2 over 2, another root 2 over 2, so minus root 2 over 2. And minus another root 2 over 2. Okay, so I'm trying to be careful. Yeah, we're almost there. Okay, finish. Let's finish. This will make root 2, right? That makes root 2. And this makes -2, -2. And this piece is negative root 2. There's another negative sign, so it's another root 2. Another root 2. Okay, so -1. So in the end, we get 2 times root 2 -2. 2 times root 2 -2. Okay, so that is the whole of the question. And I think I'm going to stop here. All right, thank you for watching.